Okay, I was interrupted again, which I guess is great about working from home. So here we go. Your next example is exercise 12. Part A is kind of a repeat of what we just did. All right, so we're going to find f such that the vector field f is the gradient of f, lowercase f. Okay, and then we're getting into our second fundamental theorem where we are going to, since this is true, okay, if we can find that, remember, if that's true, then it's conservative. Okay, and that means that we can use our second fundamental theorem to actually evaluate that integral. Okay, and that's what we're going to do then. So the vector field is given by this first expression here. Okay, so we got our x component and our y component, and we have our curve defined here also. Okay, so first things first, we do need to find f, which would be we have two ways of getting there, right? We can integrate 1 plus xy e to the xy with respect to x, or we can integrate x squared e to the xy with respect to y. Neither one of them are very pretty. We're going to have to do integration by parts regardless. That second integral will take integration by parts twice because of the x squared there. The first integral, it's only going to require it once. So we might be better off doing that, okay? I'm actually going to split it into two separate integrals because one of them would not require by parts. Okay, and that's going to be this first one here, right? You could think about it as like a u sub that it might require, but the integral of e to the x is e to the x. Okay, if I were to differentiate that, I'd have to multiply by y, which means I need a 1 over y out front. Okay. The second one's going to require by parts. I am going to take the y out since it's, since it's a constant. Okay. And then what I have left here, when I integrate it, u will be x, du will be dx, dv will be e to the xy dx, and v then is the integral of that, which I happen to have just done when I did the first integral, right? So 1 over y e to the xy. Okay. So then we're going to have y times uv, so x over y e to the xy, minus the integral of v, again, I'm going to take that y out front, du. Okay. And again, there's that integral again, the third time that we're doing it in this problem. Okay. I'm also seeing, right, that these y's are going to cancel out if I redistribute the y. Okay. So I have 1 over y e to the xy plus x e to the xy minus that integral again will give me 1 over y e to the xy. Okay, and that actually works out very nicely because the first and last terms cancel, and it's e to the xy plus, again, some function of y. Okay. All right. Now, I don't want to integrate the second one. Okay, it's integration by parts twice. I already did it by parts once. So I'm going to use that second method where f is x e to the xy plus g of y. Okay, I already know that the partial of that with respect to x will get me back to my first guy there, right? Okay, so now I'm going to find the partial of that with respect to y. Okay, the partial of that with respect to y is actually pretty easy to do, isn't it? Oh, you know what? That second integral, I was getting scared thinking about the x's. That's not a tough integral at all to do. But that's okay. Actually, if I had integrated that, right, with respect to y, so it'd be x squared e to the xy, and and then I'd have to have a 1 over x e to the xy. Not so bad, is it? Okay. We went through a real fun integration by parts when I could have just done that. That's okay, right? But again, my partial there then, with respect to y, would just be x squared e to the xy plus g prime of y. And we know that we've already got what we need, so g prime of y is 0, which means g of y is at best a constant. So f is x e to the xy plus some constant. Okay, so there's your part A. Part B now, I don't want to get too far away from the problem there. Okay, I want to integrate it. Okay, and remember, it's path independent because I was able to go through that process in A, which means I only need to evaluate at the endpoints. Okay, so all I need to do, let's see here, evaluate it from t equals 0 to t equals pi over 2. Okay, well, r of 0 will give me cosine 0 to sine 0, which is 1, 0. Okay. R of pi over 2 is going to be cosine pi over 2 to sine pi over 2. Okay, so that's going to give me 0, 2. Okay, so I only need to evaluate it at those two endpoints. So f of 0, 2 minus f of 1, 0. So I will have 0 times e to the 0 times 2 plus k minus 1 times e to the 1 times 0 plus k. Okay, and you can see the k's will cancel out every time. I really don't need to show them in my work, okay, but I just wanted to show you once. That doesn't really matter what k is. I have 0 minus 1, so my answer is -1. Okay. All right, we're going to do another one here. My Chromebook doesn't glitch out too much on me. All right. This is number 18 in your book, and I'm going to have to look at the instructions on it because I don't have it written out completely. This one says, show that the line integral is independent of a path and evaluate the integral. Okay, so integral over c sine y dx plus x cosine y minus sine y dy. Okay, and then it says C is any path from 2, 0 to 1 pi. Okay, so we can show it's path independent. And remember, we can do that by showing that your dp dx should equal dq dy. Okay. Oops, I mixed them up. The first one's with I was looking. It's always the opposite. So dp, come on, Chromebook. Don't freeze up. I'm having the hardest time with this video today. dy dx. Okay, it's always the opposite. All right, so the derivative of sine y with respect to y is cosine y. And the derivative x cosine y minus sine y with respect to x is just cosine y. Okay, so since those two are equal, it is conservative, which means it's path independent. Okay, so now I'm going to find my function. And that's another thing too, is that if we can find this function, it also is going to show us that it's conservative. Okay, but just like we did in the previous several problems, we're going to integrate sine y with respect to x, and that will be x sine y. Okay, come on. And this is going to be the first one where it doesn't just work out to be 0, okay? Plus some function of y. We can also integrate x cosine y minus sine y with respect to y. Okay, there you go. We get x sine y. All right, plus cosine y plus some function of x. Okay, and so we can see here that our g of y is cosine y. Okay, if I replace that g of y with cosine y, when I take my partial with respect to x, it's treated as a constant and it goes away. Okay, and then remember too, so that's one method that we can use. So f of xy would be x sine y plus cosine y plus some constant. Okay, the other way that we can do it, right, is once you find that f is x sine y plus some function of y, the partial with respect to y would be x cosine y plus g prime of y. Okay, and so we can see that that means that g prime of y is negative sine y. So g of y would be the integral of negative sine, which would be negative cosine, so cosine of y. Okay, and so either way, we'll get to this answer here. All right, and then your second piece there is to evaluate it from 2, 0 to 1 pi. So we'll do f of 1 pi minus f of 2, 0. So we'll have 1 sine pi plus cosine pi. And we like I said, we don't need to do that, plus k, minus 2 sine 0 plus cosine 0. Okay, so we're going to have the sine of pi is 0, cosine of pi is negative 1, minus 0 plus 1. So it looks to me like we're going to have negative 2. Oh. And that's your final answer. Okay, we're going to do another example. And again, I know that we're getting a lot of examples here. You never have to watch them all if you're getting it, but at least put me on fast forward or something. Okay, if you're seems to be catching on quickly. We're going to look at number 20. Okay, which is, I believe, a similar problem. Oh, we want to find the work done. Okay, so we have f of xy equals e to the negative yi minus x e to the negative yj. And we want the work done by this force field F in moving an object from P to Q. P is 0, 1, and Q is 2, 0. Okay, so it's really no different than what we've been doing. We can tell that it's conservative. First of all, I don't want to get P and Q mixed up, but the partial of this with respect to x, with respect to y, would be negative e to the negative y. The partial of this with respect to x would be negative e to the negative y, so we can tell that it's conservative. Okay, we can find our f. We're going to integrate e to the negative y with respect to x. Okay, so that's going to be x e to the negative y plus some function of y. Okay, and if that is f, then the partial derivative with respect to y would be negative x e to the negative y plus g prime of y. So we can see again that g prime of y would be 0. Okay, so f of xy is x e to the negative y plus some constant. Okay, evaluate it. We want to do f of 2 is 0 minus f of 0, 1. So we're going to have 2e to the negative 0 minus 0e to the negative 1. So it looks to me like we get 2 there. Okay, I am going to show you another thing that you can do there. Do I want to do this or not? I'm not sure. I think I'm going to leave it as that. Well, you know what? The reason that I have this is because it's showing how you did it in section 3.2 with just your basic line integrals. Okay, so kind of thinking back to this used to be a much more difficult problem. Okay, where when we wanted to integrate e to the negative y dx plus negative x e to the negative y dy, we had to, if you remember, you had to parameterize it. Okay, so we had to take that r of t, okay, and it was a segment. So in problem 20, it's saying no matter what the path from 0 to 1 or to 2 to 0, it doesn't matter how you get there. In section 3.2, we did it as like a line segment, and if I parameterized it, I did 1 minus t times 0, 1 plus t times 2, 0, and I would have gotten, let's see here, 2t and then 1 minus t. Okay, and that, again, remember that was from t is between 0 and 1. Okay, and so then we parameterized everything. We'd have the integral from 0 to 1, e to the negative 1 minus t. And then we had to do dx dt was 2, and dy dt was negative 1. Okay, so then I'd have e to the negative 1 minus t times 2 plus negative 2t e to the negative 1 minus t, and then multiplied by negative 1, so we change that to a positive, dt. Okay, I'm going to factor the 2 out, and I'm going to change that to be e to the t minus 1 plus t e to the t minus 1. Okay, and then this would be, again, integration by parts. Okay, so, what do I want to do here? I'm going to do it a little differently than we did the previous one. I'm going to do e to the t minus 1 times 1 plus t dt. So u is going to be 1 plus t, du is going to be dt, dv will be e to the t minus 1 dt, and then v is e to the t minus 1. Okay, so then I'd have 2 u times v minus integral of v du. So I'd have 2, 1 plus t, e to the t minus 1, minus e to the t minus 1. I apologize again for my Chromebook getting glitchy here. Okay, so then I would have 2 e to the t minus 1, and then I'd have 1 plus t minus 1, so t, when I simplify that. Okay, evaluated from t equals 0 to t equals 1. Well, when t equals 0, the whole thing is going to be 0 because of that t out front. Okay, so it's just going to be 2, and that's it. Okay, and you can see I get the same answer. All right, so we did the same type of problem in 3.2, and now you can see how if it's conservative and you can use that second fundamental theorem, it's a little bit easier. Okay, the last thing that I would just want to comment on, you have some homework problems where they show you a vector field and they ask you if it's conservative. Okay, when asked if a vector field is conservative, see if the integral along a closed curve would be 0. Okay, in general, there should be no rotation. So that's kind of a big hint to your homework problem. Okay, if you, this, I'm basically going to give it away, but that's okay. If your vector field looks like this, okay, you can see that if your closed curve is a circle, you are going to have a positive integral there. Okay, if this is your closed curve, those arrows are just always going with the path. Okay, if we're oriented the same. Okay, so that's going to give you a positive integral. All right, if you can see that, I don't want to, we have a different vector field that goes like, I'm trying to do kind of the one that's in the book for this one too. Yeah, it's very rough. Okay, but if you can draw in like a closed curve here, and you see that where you're going, don't worry too much about the background here, but if you see where you're going, like arrows kind of balance each other out, so maybe, again, if this is oriented, if your path is oriented in this direction, this counterclockwise direction, you can kind of see that like the culmination of all the arrows kind of balance each other out. This guy over here that's with the curve, oops, I should draw this the other way, balances out with this guy over here. I'm going to switch the order there. That's against you. Okay, and then maybe you have another guy over here that's kind of balanced out with a guy over here. Okay, so kind of think about, almost like for every action, is there an equal and opposite reaction, right? Okay, for just as often as an arrow's with me, is there another arrow that's against me? Okay, and that's when that line integral is going to end up being 0 on that closed curve. Okay, so look for that. And at this point too, it's very just eyeballing it. Okay, all right, thanks for putting up with my glitchy video today.